How's it going, ladies and gentlemen? It's Johnny here, looking at 12.7 and 8 electrolysis and electroplating. So objectives for this unit would be describe how electrical power can be used to cause chemical reactions, as well as label important parts of an electrolytic cell. All right, so you may be wondering at this point, we've used chemical reactions to generate electricity, but can we do the opposite? Can we use electricity to generate chemical reactions? And we can. It's called an electrolytic cell. All right, so let's break down the word electrolytic. Electro just kind of means electricity, so you've seen that probably in electricity, electrocute, etc. And lytic means to break apart. So things like lysosomes or lyse means to break it down. All right, so we're using electricity to power decomposition reactions. We need a DC power source, and it's important that it needs to be DC. You may be asking, well, what the heck does that even mean? DC stands for direct current, and AC stands for alternating current. Now, AC, this is what we have in our homes. It's what you plug things into. And here's a video to help demonstrate the difference between them. All right, so DC is direct. You have electrons going from one spot to another in a straight line, traveling all the way through. Alternating current, they go one direction, stop, and then go back in the other direction again. They're alternating which direction they're flowing, hence alternating current. All right. So decomposition is almost always non-spontaneous, meaning that if you want it to happen, you have to constantly give it energy. It could be extreme heat that can break the bonds. If you don't have oxygen around to react with it, you just heat it up and you can break stuff down. Or you can use electricity to force the metal ions to gain back those electrons that they lost when they formed a chemical bond, and reduce to metal atoms and force the non-metal ions to give up those electrons that they gained. Yeah. So here's an example. Say you got some sodium chloride and you wanted to break it down into sodium and chlorine gas. Well, you're going to have to oxidize the chloride ions. You're going to have to take those electrons away, and you're going to have to reduce the sodium ions to become the sodium metal. So the first thing that we need to do is we need to melt the sodium chloride to make sure that the ions can move around and the stuff will actually conduct electricity. All right, so you melt it. Then you got to put in electrodes. Usually they use graphite because it's got a high melting point and it's non-reactive. So you can put the graphite into molten sodium chloride and it won't react with the sodium chloride. You hook those up to a battery, and over here you see we got the anode on the left and the cathode on the right. So the anode is where oxidation occurs and electrons are going to come out of the battery and they're going to build up onto this graphite rod. So now we have negative electrons, which are going to attract the positive sodium ions and reduce them. All right, so those sodium ions are going to pick up those electrons and they're going to be reduced to become just sodium metal, which is going to build up at that electrode. You're going to get a bunch of pure sodium forming there. Now the opposite is going to happen over here. We're going to oxidize the chloride ions. The chloride ions have these electrons. They're going to be attracted to the positive electrode, where they're going to be stripped of those electrons. So that electrode is going to steal those electrons. They're going to complete the circuit to the voltaic cell, and the chloride ions are going to become chlorine gas, and it's going to bubble as a green, poisonous, toxic gas. All right, don't breathe that stuff in. All right, cool. You can do the same thing with water, get hydrogen and oxygen. A little more exciting. Probably do that in class. So water you can break down to hydrogen gas, which is explosive, and oxygen, which, is what you need to make it explode. So you do pretty much the same thing. You have water. It's already liquid, so you don't got to melt it, but you do need to add some acid so that it will conduct. So you do the same thing. You put some graphite electrodes into it. So graphite being non-reactive, you don't have to worry about it reacting with stuff. Hook it up to a battery. Again, electrons come out of the negative end, and they're going to build up on that electrode, and they're going to attract the H plus ions that are in the water. Right? So the H plus is going to become reduced and become hydrogen gas, and that's going to bubble up. It's going to do that as long as you have it hooked up. The opposite is going to happen on the other end. The oxygen ions are going to be attracted to the positive electrode, and you're going to strip away those two electrons that they gained, completing the circuit for the voltaic cell. And then you're going to get oxygen bubbles forming there. You can trap them if you have tubes, trap them so that the gases build up and fill those tubes, and you will see that you get twice as much hydrogen gas as you do oxygen gas. Well, that only makes sense because you use twice as much hydrogen in water than you do oxygen. And then there's electroplating, which is pretty cool. Same kind of setup again. You have a voltaic cell to power the whole thing. You need a DC power supply. You have the thing that you want to coat in the metal attached to the anode at the positive end. I'm sorry. You attach the metal to the negative end of the voltaic cell, the anode. And then you attach the thing that you want to plate it with, like say you wanted to silver plate some silverware, to the cathode of the voltaic cell. And then you immerse the whole thing in a solution that has the ion of the thing you want to plate. So here, silver ion. All right, so the metal is going to oxidize. The metal is going to lose its electrons. And the voltaic cell is going to shoot out electrons out of its anode. It's going to build up on the thing that you want to plate. See, this is going on over and over. Silver loses electrons at its anode, the electrolytic cell's anode. Goes to the cathode for the voltaic cell. Voltaic cell anode loses electrons and comes out onto the thing that you want coated. So now we got a bunch of negative charge here attracting the silver ions, which is going to reduce the silver ions as silver metal, which is going to bind to it. So the longer you run, the thicker coat of silver you would get. So the big idea is, kind of gets confusing, but the big idea is voltaic cell, we use chemical energy to make electrical energy. Electrolytic cells, we do the opposite. We use electrical energy to make chemical energy, or chemical reactions occur. So we need a DC power supply. It's non-spontaneous, meaning we got to keep giving it energy. Things that are the same. The anode is still where oxidation occurs, so that an-ox mnemonic still works. The cathode is still where reduction occurs. And electrons always flow from anode to cathode. All right, let's take a look at some practice. Actually, you know what? Let's save that for class. I'll see you guys there. Bring